we've seen how to solve inequalities involving linear expressions on both sides of the inequality, but let's talk about how we can solve quadratic and rational inequalities, which are more complicated and require a slightly different technique. Although, again, the analogy with how we solve quadratic and rational equations will be helpful as we move through the process. So, let's start with quadratic. A quadratic inequality has the form ax squared plus bx plus c is greater than or equal to 0. The first thing that we have to remember when working with quadratic inequalities is that we need to get 0 on one side. So before we do anything else, we need to have 0 on one side. From there are a few techniques that can be used here. I'm going to talk about two of them. We're going to talk about creating intervals and testing them, and we're going to be talking about looking at the signs of the various factors involved in your expression. So the first step is going to be to get 0 on one side. And so let's talk through the first method. So method 1 for solving such an inequality is first we want to find the solutions to the equation ax squared plus bx plus c equals 0. And we can do this using factoring or the quadratic formula, whichever is appropriate to the problem. What this will do is it will break up the number line. We're going to find our two solutions, and they'll sit somewhere on the number line. So we've got a solution, or often two solutions. And these are where, these solutions are where the expression on the left, the quadratic expression, equals 0. Now the point here is that between the solutions, or in other words, on the intervals defined by them, the expression ax squared plus bx plus c is always either positive or negative. So in other words, in the first interval we have over here, the expression ax squared plus bx plus c will either be always positive or always negative. If it's always positive on that interval, then that tells us that that interval contains solutions to the inequality that we wrote down above, because I was looking for a greater than or equal to. On the other hand, if the values over here are always negative, then those numbers aren't solutions to the inequality we're working with here, because it's a greater than or equal to. Of course, knowing that they're always positive or negative doesn't help us unless we have a way of figuring out what it is. We tell what kind of interval it is, either positive or negative, by testing a point in it. So let's see an example to see how this works and to flesh out the process. So let's solve the equation x squared plus x minus 6 is greater than or equal to 0. So, first step will be to solve the equation x squared plus x minus 6 equals 0. We want to know where the expression x squared plus x plus 6 is greater than or equal to 0. The first step is going to be figuring out where it's equal to 0. And actually, let me change this to be just a strict greater than. I don't want to give the impression that there's any difference in how we do this, depending on whether it's a greater than or a greater than or equal to. The only difference will show up right at the very end, and I'll call it out. So step one will be to solve the equation that we get when we just replace the inequality with an equality. So this we're familiar with. This equation actually factors because we can take 3 and negative 2. Those are two numbers that multiply to equal negative 6 and add to equal 1, the coefficient of the x term here. And so we get that x plus 3 is equal to 0, or x minus 2 is equal to 0. And from there we get that x is equal to negative 3, or x is equal to 2. So that splits our number line up into 3 intervals. So our intervals are the interval from negative infinity to negative 3, the interval from negative 3 to 2, and the interval from 2 to infinity. And the point is that in each one of these intervals, either all of the numbers are solutions to our inequality or none of them are. The reason for that is basically because as we look at the values of the expression x squared plus x minus 6, as we move along the number line, we look at small values of x and then look at bigger ones, bigger ones, bigger ones. As we move to the right, the only time that the values can switch from being positive to negative are when the equation equals 0. And that only happens at negative 3 and 2. So now what we want to do is to test each interval to see whether it contains solutions or not. And the way that we do this is we're going to pick one value from each interval and test it. So we're going to pick some number from the first interval, some number from the second interval, and some number from the third interval, and plug those into the original inequality to see whether that number makes the inequality true or not. Typically, you want to choose easy numbers to work with, so that usually means small numbers, although not always. And when 0 is a possibility to choose, you pretty much always want to choose that. So I'm going to be using 0 to test this middle interval, and I'll go ahead and use negative 4 to test this left interval, and 3 to test the right interval. So let's test x equals 0. So what I'm going to do there is I'm going to use the original inequality and plug 0 in. I'm going to get 0 squared plus 0 minus 6 is greater than 0 when I plug 0 in for x, and I ask, is this statement true or not? And this is clearly not true. The left-hand side turns into negative 6, the right hand is 0, so that's not true. Now, this means that 0 is not a solution to our inequality. But all of the elements of the interval from negative 3 to 2 have to have the same solutionness to the inequality. They either have to all be solutions or none of them are solutions. And because 0 is not a solution, that means that none of the interval from -3 to 2 is a solution. So that means that we can say that this interval is not a solution to the inequality. Well, let's keep going. Let's test x equals -4. For this, we'd get -4 squared plus -4 minus 6 is greater than 0. Simplifying that, we get 16 minus 4 minus 6 is greater than 0. 16 minus 4 is 12, minus 6 is 6, is greater than 0. That is true. So that tells us that -4 is a solution. So -4 is a solution, and that means that all of the numbers in the interval from -infinity to -3 are solutions. Because they are either all solutions or none of them are. -4 is a solution to the inequality, therefore all of the numbers in that interval are. And similarly, we can test x equals 3. Get 3 squared plus 3 minus 6 is greater than 0. That's going to be 9 plus 3 is 12 minus 6. We get 6 is greater than 0. Check. So the interval from 2 to infinity is also part of our solution. Now, a very important point here as you're going through this process, your endpoints, your places where your expression equals 0, the -3 and the 2, are never numbers that you can test with. They're not useful to test. You already know that if you plug them into your inequality, you're going to get 0 out of it, and that's not useful. You need to pick numbers between the solutions that you've come up with for your equation corresponding to your inequality. So that means that we've got 2 intervals that contain solutions. And so we can start graphing out our solution this way. We're going to include all the numbers from -infinity to -3, all the numbers from 2 to infinity. And then the question is whether we include -3 and -2. And here's where the difference between the strict and weak inequalities come in. So because this is a strict inequality, this means that we are not going to include the 2 endpoints. Because the endpoints were where the quadratic expression equaled 0, and we're trying to find the places where the quadratic expression was greater than 0. So we're not going to include -3 and 2. So the green intervals on the number line are what our solution would look like for this problem. If we wanted to write down the solution in interval notation, we would use a new symbol that we haven't used before. In this case, we've got the 2 intervals, -infinity to -3 and 2 to infinity, and we want to include all of those numbers together. So what we do is we include this symbol here, sort of a horseshoe shape. This symbol is the mathematical operation of union, and it means take all the things that are in the left set and in the right set and include all of those together. So in this case, our solution is a union of 2 intervals, and anything in either one of the intervals is a solution to our inequality. All right, let's look at the other common way we have of solving quadratic inequalities. So let's solve. Let's do x squared plus 5x plus minus 24 is less than or equal to 0. So the next method that we have involves factoring the quadratic expression to see where each factor is positive and negative. So for this problem, we'll take our inequality x squared plus 5x minus 24 is less than or equal to 0 and factor the left-hand side. Now the left-hand side factors as x plus 8 times x minus 3 is less than or equal to 0. Now what we're going to do is we're going to create sort of a table. We're going to take a number line again. It's going to look sort of similar to how we worked things out before. But now what we're going to do is we're going to look at these two factors, x plus 8 and x minus 3, and indicate where these expressions are positive, negative, and 0. So we're going to write where each of these are positive, negative, or 0, given this number line here. So I'll just go ahead and indicate a 0 on the number line to calibrate us here. So let's start with the expression x plus 8. We know that the expression x plus 8 will be 0 when x is negative 8. So when x is negative 8, this expression, x plus 8, will be 0. Now, if x is more than negative 8, if x is big, then x plus 8 will be positive. So we'll indicate that this way. On the other hand, if x is less than negative 8, if x is small, then it will be negative. So this sort of gives a visual representation of what's happening with the individual factor x plus 8. It starts off negative, and then it gets to 0 when x is negative 8, and then it's positive afterwards. We're going to do the same thing with x minus 3. X minus 3 is going to be equal to 0 when x is equal to 3. Now, if x is bigger than 3, then x minus 3 is going to be positive. But if x is less than 3, then x minus 3 is going to be negative. So the point here is that we can now use this information of positives and negatives to say where the product is going to be positive or negative. So now we can look at the product x plus 8 times x minus 3, which is the expression that we're interested in. So we remember that when x plus 8 is equal to 0, well, 0 times anything will be 0. So if x is equal to negative 8, then the product of x plus 8 and x minus 3 will be 0. Similarly, if x minus 3 is 0, then their product is going to be 0. So we know that x plus 8 times x minus 3 is going to be 0 when x is equal to negative 8 or positive 3. But now we can look at where the product is going to be positive or negative. So let's look at the first interval here, the leftmost interval. On the leftmost interval, x plus 8 is going to be negative, and x minus 3 is also negative. Therefore, their product is a negative times a negative, which is a positive. So the expression x plus 8 times x minus 3 will be positive when x is less than negative 8. On the other hand, between negative 8 and 3, notice that the factor x plus 8 is positive, but the factor x minus 3 is negative. Therefore, their product is a positive times a negative, which is a negative. Finally, if x is greater than 3, if we're on the right-hand side of this diagram, then x plus 8 and x minus 3 are both going to be positive, and therefore their product is also positive. So this gives us an indication of where our expression that we care about, x plus 8 times x minus 3, is positive, negative, or 0. So now we can start identifying where it satisfies the condition we want, namely being less than or equal to 0. And we see that that's going to occur for this region here. This region between negative 8 and 3 is where x plus 8 times x minus 3 is either 0 or negative, which is what we were looking for. We were looking for where x plus 8 times x minus 3 is less than or equal to 0. Therefore, that tells us that our solution is going to be between negative 8 and 3 over here, including negative 8 and 3 in both places, because we're dealing with a weak inequality and we want to include the values of x where the expression actually equals 0. So our solution in interval notation is going to be the interval from negative 8 to 3 with brackets on both the left and the right. So this is another technique that we can use. We can break down an expression into factors and then compare where each factor is positive, where each one is negative. A few things to point out about this method. First of all, just like with the first method, you need to get 0 on one side of the inequality first. If your expression starts off and it doesn't have 0 on one side, you need to gather all of your terms over to one side so that you do have 0 on one side before you can begin. Next, about this method required us to factor. If we are working with a quadratic inequality and we can't factor the quadratic expression, then we might have to use the quadratic formula in order to get the solutions to the quadratic equation, in which case we want to use method 1. If your quadratic expression doesn't factor, just use method 1. Just write down what your two solutions are on the number line and test intervals, the way that we did back on the previous example. So that's how we solve quadratic inequalities. Let's talk about solving rational inequalities. And it's going to be similar. We're going to be able to use basically the same two methods. We're just going to have a couple of little twists that we need to be careful about. So solving rational inequalities. So rational inequalities would be something like x squared plus 2x plus 1 over, let's say, x minus 3 is greater than or equal to 0. Now, just like with the quadratic inequalities, we need 0 on one side, no matter which method that we're using. So let's start with method 1. which is going to be very similar to the to method 1 previously, but here we need to consider both the numerator and the denominator. So method 1 is going to be to find the zeros of both the numerator and denominator. And that means, i.e., set each of the numerator and denominator equal to 0 and solve. And then use that to split up the interval and then test. And then test to see whether split up the real number lines into intervals, I should say. So split up the number line into intervals and test each one. All right, so let's take our example right here. So we need to find all the places where both the numerator and the denominator equals 0. This is very important because the rational expression can change sign. It can go from positive to negative or vice versa, anywhere where either the numerator or the denominator is 0. So we need to do both of those. So we can get x squared plus 2x plus 1 equals 0 for the numerator. And that factors as x plus 1 times x plus 1 equals 0. So we get x plus 1 equals 0, or x plus 1 equals 0, which is the same thing. So we get x equals negative 1. So that x equals negative 1 is the place where the numerator might be equal to 0. And then the denominator, we'll take x minus 3, set it equal to 0, and add 3 to both sides, get x equals 3. So that means that our number line gets split up as follows. In this case, we only have 2 numbers to work with, so it's kind of similar to what we had before, where we've got negative 1 and 3 splitting up our number line into 3 intervals. An interval from negative infinity to negative 1, from negative 1 to 3, and from 3 to infinity. And now we're going to test a number in each interval. So I'll go ahead and test negative 2. I'll test 0 because when 0 is an option, you should always take it. And we'll test 4. So let's do that. Over here. So let's get x equals 0. That'll give us 0 squared plus 2 times 0 plus 1 over 0 minus 3 is greater than or equal to 0. But that gives us a numerator of 1 and a denominator of negative 3. 1 divided by negative 3 is not greater than or equal to 0. So that's a failure. That means that the interval containing 0 does not contain solutions to the inequality. Well, let's look at x equals negative 2. If we get negative 2 squared plus 2 times negative 2 plus 1 over negative 2 minus 3, and we want that to be greater than or equal to 0, well, the numerator here is going to be 4 minus 4 plus 1, and then negative 2 minus 3 is negative 5, and negative 5, is that greater than or equal to 0? It is not. So that means that the interval from negative infinity to negative 1 is also not a solution. So let's check x equals 4. That'll give us 4 squared plus 2 times 4 plus 1 over 4 minus 3. Is that greater than or equal to 0? Well, 4 squared is 16, plus 8 is 24, plus 1 is, we get 25 over 1, greater than or equal to 0, and that does check out. So that tells us that in this case we had 3 intervals, and two of them do not contain solutions, and one of them contains, and one of these intervals contains solutions. All right, so then we're almost ready to give our answer, but there's a couple little wrinkles that we have to check on. So, first of all, when it comes to this interval on the right, we need to come over here and see whether we ought to include 3. So the best thing to do with rational inequalities is to just plug that number back into the inequality and see whether you get a true statement or not. Now, the reason for this is that there are a few things that can go wrong. With a quadratic inequality, when we see this greater than or equal to, meaning that it's a weak inequality, that typically means that we're going to be including the endpoints of our intervals. However, with rational inequalities, we can get some strange things happening. So, for instance, we can get something like the following. So if we test x equals 3 in our expression, we get 3 squared plus 2 times 3 plus 1 over 3 minus 3. And no matter what, this inequality is going to be false because we've got a 0 in the denominator. Anything that would make a denominator equal to 0 is never a solution to anything. So this means that 3 is not a solution, even though we were dealing with a weak inequality here. So that means that we've got an interval that looks like this over here. Now, the next thing is one that actually can come up in the quadratic inequalities, and we should test this even when we're working with quadratic inequalities and something like this comes up. So look at the number -1 right here. Now, it sits between two intervals that don't contain solutions. However, it might still be a solution when you're dealing with a weak inequality. So the point is to check all of your endpoints, all the points that you came up with in order to split your interval into inequalities, or split your number line into intervals. Sorry, check all of those endpoints, basically no matter what. So if x is equal to 1, we get 1 squared plus 2 times, or sorry, not 1, but -1. So if x is -1, we get -1 squared plus 2 times -1 plus 1 over -1 minus 3. And this is true because this makes the numerator here work out to be 0. And so the whole fraction is 0, which means that 0 is greater than or equal to 0. So that means -1 is a solution. So in this case, we've got a weird case where we've got an interval as part of our solution, and then a single point over here. This -1 over here is an additional solution to the inequality, which is just sort of sitting by itself and doesn't have an interval to go along with it. So the way we would express this in our solution is the following. Well, first of all, we would definitely have our interval from -3 to infinity, not including, from 3 to infinity, not -3. From 3 to infinity. And so that takes care of the right-hand part there. But then we have a union with, and now we've just got the single number -1. And the way that we indicate that is using our set notation back from when we were first talking about solution sets, and so we'll use the notation curly braces around -1. So this is the set of all numbers that make this rational inequality true. All right, let's do one last example where we use the second method for solving rational inequalities, which works very similarly to method 2 from quadratic inequalities. So let's solve the equation x squared plus 3x plus 2 over x squared minus 7x plus 10 is less than 0. So method 2 will be to factor the numerator and denominator completely. Then identify where each is positive and negative to determine the sign of the whole expression. So just like we did last time with the quadratic expression, we want to look at this rational expression, factor the numerator and denominator, and then figure out what's happening with each of those factors. So in this case, the numerator factors as x plus 1 times x plus 2. The denominator factors as x minus 2 and x minus 5. And we want to know when this expression is less than 0, is negative. So let's go ahead and do that. Now this is the most complicated of these expressions that we've had so far. We've got 4 different factors that we want to look at: x plus 1, x plus 2, x minus 2, and x minus 5. And for each one of these, we want to identify on the number line where they're positive and where they're negative. So let's work from the bottom up here. X plus 1 is 0 when x is -1. So when x is -1, the expression x plus 1 is 0. If x is greater than that, then the expression x plus 1 is positive, and if it's less than that, it's negative. The expression x plus 2 is going to be 0 when x is -2. It's going to be negative when x is less than that, and positive when x is greater than that. The expression x minus 2 is going to be 0 when x is 2, negative when x is less than 2, and positive when x is greater than 2. And then finally, x minus 5 is going to be 0 when x is 5, positive when x is greater than 5, and negative when x is less than 5. So now what we're going to do is we're going to look at what happens on each of these 5 intervals now, defined by the places where each of these factors are 0. So now we want to see, given all these signs, positives, negatives, and zeros, what happens when we look at the expression x plus 1 times x plus 2 over x minus 2 times x plus 5. Well, let's start with the places where things are 0. If x plus 1 or x plus 2 is 0, that means that the whole expression is going to be 0, because those are in the numerator. On the other hand, if x minus 2 or x minus 5 is 0, the whole expression will be undefined. So I might put a u there for undefined. Now, in particular, what that means is that 2 and 5 are never going to be solutions to this, no matter what. Now we can look at each one of our intervals here, from negative infinity to negative 2, negative 2 to negative 1, negative 1 to 2, 2 to 5, and 5 to infinity, and see whether the whole expression here will be positive or negative. Now, the good thing is that the rules for when you get a positive or negative product don't care about whether the positive or negative is in the numerator or denominator. We just have to see, well, what happens if we take say 4 negative things and multiply and or divide them together. So on the first interval here, we've got a negative, 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 and negative, and 4 negatives make positive. Next one, we've got negative, positive, negative, negative, and so that'll be negative there. Then we've got, on the next interval, positive, positive, negative, negative gives positives. Then positive, 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 negative is negative, and then all positives over here. So now our solution can be gotten by identifying where the expression x plus 1 times x plus 2 divided by x minus 2 times x minus 5 is less than 0. This problem is asking for things to be strictly less than 0. So that's going to happen on this interval and this interval. So in this case, we've got 2 intervals we're working with. Do note that if this were a weak inequality, if this said less than or equal to 0, we would include these zeros over here on the left, but we would never include the undefined points in our diagram. So for us, the solution is from negative 2 to negative 1, union with the interval from 2 to 5. Those are the intervals where this rational inequality, or this rational expression rather, is less than 0. One last point before we finish up. When you are using this method 2, which can be quite powerful, you need to pay close attention when you have a repeated factor. So, for instance, let's choose a very simple problem to look at. Let's suppose that we have the expression x minus 2x plus x squared minus 2x plus 1 is greater than or less than or equal to 0. So if we want to use method 2, what we would do is we would factor this left-hand side. Now this left-hand side factors as x minus 1 times x minus 1. It's less than or equal to 0. Now the trick here is when you have a repeated factor, you have to include both of them here. So even though their pattern of positives and negatives and zeros are going to be exactly the same, because of course they're exactly the same factor, you need to include both of them. So you need to include all copies of a repeated factor. Now, when we do that, we can finish things up pretty quickly because these are both going to be 0 at 1, and they're going to be negative to the left of 0, positive to the right of 0, And now that means that on the interval from negative infinity to 1, their product will be positive because it's a negative times a negative. And on the interval to the right of 1, it's also going to be positive. So if we're looking for the place where this expression, quadratic expression, is less than or equal to 0, well, it turns out there's actually only one spot where that happens. So the solution in this case is just going to be a single number. It's just going to be 1. So it is possible for inequalities to have just a single solution. Notice also that if I had asked for the inequality x squared minus 2x plus 1 is less than 0, this has no solution. If you look at the diagram we've got, there are no places on the real number line where the expression x squared minus 2x plus 1 is negative. It's always at least 0. So inequalities can have just one solution sometimes. They can also just have no solutions at all. Lots of possibilities exist when you're working with inequalities.